Logistic regression is our first step from classic statistics into modern machine learning. In this session, we will learn how to predict binary outcomes, turn linear scores into probabilities with the sigmoid function, and see why logistic regression can be viewed as a mini neural network. We will work with a real marketing example, build a model in Colab, and connect everything to the activation functions you will see again in deep learning. Here, we start with a simple definition of logistic regression. Logistic regression is a statistical method for classification, where the outcome is a category such as 0 or 1, yes or no, churn, or stay. Instead of predicting a raw number, it predicts the probability that a case belongs to the class labeled 1. On the right, you can see the difference from linear regression. A straight line can go below 0 or above 1, while logistic regression uses an S-shaped curve so that all predicted values stay between 0 and 1 and can be interpreted as probabilities. On this slide, I want to compare linear regression and logistic regression side by side. Linear regression is used when the target variable is continuous, such as house price or sales revenue. Its output can be any real number, and we usually just take that number as the prediction. Logistic regression is different. The target is binary or categorical, for example, spam or not spam, churn or stay. The model outputs a probability between 0 and 1, and then we apply a threshold, often 0.5, to decide whether the prediction is class 0 or class 1. On the right, you can see the pumpkin example. For linear regression, the model predicts a continuous value that changes smoothly with pumpkin size. For logistic regression, the model predicts the probability that the pumpkin is orange, and the decision boundary separates orange from not orange based on that probability. Now, we look at how logistic regression actually works in practice. Logistic regression predicts the probability of an outcome, such as purchase or no purchase. First, the model creates a numeric score from the inputs. Then it passes that score through the sigmoid function, which turns any real value into a number between 0 and 1 that we can read as a probability. Next, we compare that probability to a threshold, often 0.5. If the probability is above the threshold, we predict the positive class, for example, purchase. If it is below the threshold, we predict the negative class, no purchase. You can think of a marketing example. Given a customer's age, income, and past purchase history, the model outputs the probability that this customer responds to an email campaign, and we use the threshold to turn that probability into a yes or no decision. Logistic regression uses a function called the sigmoid to turn a raw score into a probability. You can picture it as a smooth S-shaped curve. When the input score is very negative, the output of the sigmoid is close to 0. When the score is very positive, the output is close to 1. Around the middle, near 0, the curve is steep and the output is about 50%. This behavior is exactly what we want because it guarantees that every prediction from the model stays between 0 and 1, so we can interpret it as a probability. The same sigmoid curve is also used in many deep learning models as an activation function for binary classification. Odds tell us how likely success is compared to failure. You can think of it as probability of success divided by 1 minus that probability. In logistic regression, we do not model the probability directly. Instead, we model the log of the odds as a linear function of the features. When a coefficient is positive, it increases the odds of the event. For example, if a coefficient is about 0.7, the odds of the event are roughly doubled compared to when that feature is 0. Logistic regression learns by adjusting its weights and intercepts so that its predictions get closer to the true labels. To do this, it uses an optimization method called gradient descent, which you can imagine as rolling a ball down a hill until it reaches the bottom. At each step, the algorithm looks at the direction that most reduces the error and moves a small step that way, then repeats. The learning rate controls how big each step is. Small steps are slow but safe. Very large steps can overshoot the minimum. Training is considered converged when the error stops improving in a meaningful way. Logistic regression is especially useful in marketing because it predicts the likelihood of an outcome for each customer. For an email campaign, it can estimate the probability that a customer will respond using features such as age, past interactions, and region. For digital advertising, it can predict whether an ad view or a click is likely to lead to a purchase based on time on site or previous clicks. For customer churn, it can estimate how likely a customer is to leave the service using information like subscription length, complaints, or discounts received. In all of these cases, the model gives us a probability for each customer, so we can rank them and focus our marketing efforts where they are most likely to pay off. Imagine a simple marketing question. After seeing an ad, will this customer actually buy the product? Here, each dot on the right is a customer. The horizontal and vertical axes represent two features, for example, age and browsing or purchase behavior. Blue points might be non-buyers and red points buyers. Logistic regression learns a straight decision boundary that separates the two regions, the blue area and the red area. For any new customer, we plug in features such as age, gender, browsing history, and past purchases. The model outputs a probability. For example, this customer has a 70% chance of buying. Then we can decide whether to target that customer with an offer or not based on that predicted probability. In this first Colab part, we focus on getting the churn data ready for modeling. We start by importing the standard data science tools, pandas and NumPy for data handling, scikit-learn utilities for splitting the data, building a logistic regression model, scaling features, and computing evaluation metrics, plus matplotlib and seaborn for simple plots. Next, we download the bank customer churn dataset as a zip file, unzip it into a data folder, and load datachurn.csv with pandas. When we call info and head, you can see there are 10,000 rows and 14 columns, including customer IDs, demographics such as geography, gender, and age, financial variables like credit score, balance, and estimated salary, engagement variables such as tenure, number of products, and whether the customer is active, and finally, the exited column, which tells us whether the customer churned or not. Exited is the target we want to predict. We then take a quick look at the distribution of exited. Most customers have a value of 0, meaning they stayed, and about 20% have a value of 1, meaning they churned. This tells us the data is somewhat imbalanced, with churn being the minority class. After that, we begin basic preprocessing. We drop ID-like columns that do not help prediction, such as row number, customer ID, and surname. We convert the categorical variables, geography and gender, into dummy variables using one-hot encoding so that the model can use them as numeric inputs. This leaves us with a clean table of numeric features. Finally, we define X and Y. The target Y is the exited column, and X contains all the remaining feature columns. We split the data into a training set and a test set, using about 80% for training and 20% for testing, and we stratify by Y so that the churn ratio is similar in both sets. Then we standardize the features with a scaler, fitting it on the training data and applying the same transformation to the test data. At the end of part 1, we have X-train scaled, X-test scaled, Y-train, and Y-test ready so we can train a logistic regression model in the next step. In part 2, we let the logistic regression model learn from the data and we generate predictions on the test set. We start by creating a logistic regression model from scikit-learn and fitting it on the training data. We pass in the scaled training features and the churn labels. During this step, gradient-based optimization runs in the background and adjusts the weights and the intercepts so that the predicted churn probabilities match the true exited values as closely as possible on the training set. Once the model is trained, we move to the test set. For every customer in X-test scaled, we ask the model for the predicted probability of churn. The model returns a number between 0 and 1 for each row, which we can read as, according to this model, how likely is this customer to churn? Next, we convert these probabilities into class labels. We use the default decision rule. If the churn probability is at least 0.5, we predict class 1, meaning the customer will churn. If it is below 0.5, we predict class 0, meaning the customer will stay. To make this more concrete, the notebook shows a small preview table with the first few test customers. For each customer, we display the true label, the predicted churn probability, and the predicted class based on the 0.5 threshold. This makes it clear that logistic regression is not just saying yes or no. It ranks customers by risk using probabilities, and then the threshold draws the line between churn and non-churn. There is also an optional cell that tries a lower threshold, for example 0.3. When we compare predictions with 0.5 and 0.3, we can see that a lower threshold marks more customers as potential churners, which usually increases the chance of catching true churners, but also increases the number of false alarms. By the end of part 2, we have a trained model, churn probabilities for each test customer, and binary predictions based on a chosen threshold. In the next part, we will summarize how well these predictions match the true labels using a confusion matrix and evaluation metrics. Logistic regression comes with a few simple assumptions that are good to keep in mind. First, it assumes an approximately linear relationship between the input features and the probability of the outcome. For example, as a customer's income increases, the likelihood of purchasing might steadily increase as well. Second, it assumes independent observations. Each row in the dataset, such as each customer, is treated as separate and not directly influencing the others. Third, it prefers no strongly correlated features. If we include almost duplicate information like total spending and average spending per visit, the model can get confused about which variable is really driving the effect. Finally, logistic regression works best with a sufficient amount of data so that it can detect stable, meaningful patterns instead of random noise. Logistic regression is a very useful model, but it is not perfect. It only captures relationships that are roughly linear in the log odds, so if the true pattern is highly nonlinear, a simple logistic model may miss it. It is also sensitive to outliers and to features that are highly correlated with each other, which can make the coefficients unstable. And when the classes are very imbalanced, for example when churners are a small minority, performance can drop if we do not handle that imbalance carefully. On the positive side, logistic regression is ideal when the outcome is binary and we want clear, interpretable probabilities and coefficient effects. It is also an excellent starting point in practice. A simple, fast, and transparent baseline model that we can compare more complex methods against later. When we build a logistic regression model, we cannot just trust it because it ran without an error. We need to evaluate it to check whether its predictions are actually useful. Evaluation answers two main questions. First, how many of the predictions are correct? So overall, is the model doing a good job on this data set? Second, when the model is wrong, what kinds of mistakes does it make and how serious are those mistakes for our business problem? These questions guide which metrics we look at next, such as the confusion matrix, accuracy, precision, and recall. A confusion matrix is a simple table that summarizes all of the model's predictions. Along one side we have the actual class, for example churn or no churn, and along the other side we have the predicted class. When the model predicts positive and the customer is actually positive, that is a true positive. When the model predicts positive, but the customer is actually negative, that is a false positive. When it predicts negative and the customer is actually negative, that is a true negative. And when it predicts negative, but the customer is actually positive, that is a false negative. Looking at these four numbers together tells us not only how often the model is right, but also what kinds of mistakes it makes. This is why the confusion matrix is the starting point for metrics like accuracy, precision, and recall. When we evaluate a classification model like logistic regression, there are four very common metrics we look at. First is accuracy. Accuracy is simply the percentage of all predictions that are correct. If the model makes 100 predictions and 80 of them match the true label, the accuracy is 80%. This is a good summary number when the classes are fairly balanced. Second is precision. Precision focuses only on the cases the model predicted as positive. For example, this customer will churn. It answers the question, out of all the customers we flagged as positive, how many were actually positive? Precision matters when false positives are costly, such as marking legitimate emails as spam or sending an expensive offer to people who would never buy. Third is recall, also called sensitivity. Recall looks at the actual positives and asks, out of all the customers who truly churned, how many did we correctly catch? This is important when missing positives is costly, for example, failing to detect a disease or missing high-risk churners. Finally, the F1 score combines precision and recall into a single number by taking their harmonic mean. It is useful when the dataset is imbalanced and we care about balancing both kinds of errors rather than just maximizing accuracy. Now we want to see how well our logistic regression model is actually performing on the test set. To do that, we start by building a confusion matrix. The confusion matrix compares the true labels with the predicted labels and counts how many cases fall into each of four boxes. True negatives are customers who stayed and were correctly predicted to stay. True positives are customers who churned and were correctly predicted to churn. False positives are customers who stayed but were predicted to churn. False negatives are customers who churned but were predicted to stay. In the notebook, we compute this matrix and draw it as a heat map. The diagonal cells, true negatives and true positives, show the correct predictions. The off-diagonal cells, false positives and false negatives, show the mistakes. You should pay special attention to false negatives in a churn problem because those are customers who left but we did not catch them in advance. From this confusion matrix, we calculate three key metrics: accuracy, precision, and recall. Accuracy is the simplest one. It is the proportion of all predictions that are correct, so it answers the question, out of all customers in the test set, how many did we classify correctly? Precision focuses only on the customers we predicted as churners. It answers, out of all the customers that the model flagged as churners, how many truly churned? High precision means that when the model raises a red flag, it is usually right. Recall, also called sensitivity, focuses on the actual churners. It answers, out of all customers who truly churned, how many did the model correctly flag as churners? High recall means we are missing fewer churners. The notebook prints these numbers and also shows the full classification report from scikit-learn, which includes precision, recall, and F1 score for both the stay class and the churn class. Together, the confusion matrix and these metrics tell us not only how accurate the model is overall, but also what types of errors it is making and whether that pattern of errors is acceptable for a marketing churn application. In the last part of the Colab, we move from pure prediction to interpretation. We want to understand which features are associated with higher or lower churn risk in this dataset. Logistic regression gives us one coefficient for each feature. To turn those coefficients into something easier to interpret, we compute odds ratios by taking the exponential of each coefficient. An odds ratio greater than 1 means that higher values of that feature are associated with higher odds of churn, holding all other features constant. An odds ratio less than 1 means that higher values of that feature are associated with lower odds of churn. The notebook collects all coefficients into a table, adds the odds ratios, sorts them, and then plots them as a bar chart. This plot lets us see at a glance which variables have the strongest positive and negative associations with churn. For example, in this dataset, older age has an odds ratio clearly above 1. That means, compared with younger customers who are similar on other variables, older customers have higher estimated churn odds. Customers in some regions may also show higher or lower odds compared with the baseline region defined in the dummy coding. On the other hand, being an active member has an odds ratio well below 1, which means active members are much less likely to churn than otherwise similar inactive members. It is important to emphasize that these are patterns in this particular dataset and model, not universal truths. But they are still very useful for marketers because they highlight which customer attributes are most strongly linked to churn and where interventions might be most effective. Finally, the notebook wraps up by connecting everything back to the theory. We saw that logistic regression takes a linear score, passes it through a sigmoid function to get a probability, and then uses gradient-based training to fit the model. In Colab, we used that model to predict churn, evaluated it with a confusion matrix and metrics like accuracy, precision, and recall, and then interpreted the coefficients through odds ratios. These are exactly the same building blocks that appear in many deep learning models for classification. Linear layers that compute scores, activation functions such as the sigmoid, loss functions based on cross-entropy, gradient-based optimization, and evaluation using confusion matrices and classification metrics. So, by understanding logistic regression well, you are building a solid foundation for more advanced neural network models in future courses. To wrap up, let's connect everything back to the big picture. Logistic regression is our basic model for binary outcomes. It takes a linear score built from the inputs, passes that score through the sigmoid curve, and turns it into a probability between 0 and 1. We then choose a threshold to convert that probability into a final 0 or 1 decision, such as churn or no churn. The model is trained by minimizing a loss based on cross-entropy, using gradient descent to adjust the weights step by step. Deep learning simply builds on the same ingredients: multiple linear layers stacked together, activation functions such as sigmoid or real U applied after each layer, and the same cross-entropy style loss optimized by gradient descent. If you understand logistic regression well, you already understand the core building blocks of modern neural networks.